Think forward. Think Research Channel.
We began the program today by talking about something called Project IceCube. It's a $270 million international effort. More than 20 collaborators are working with faculty and researchers here at the University of Wisconsin on this project. And it has to do with capturing neutrinos at the South Pole. With me in the studio today, Robert Paulus, who is UW-Madison researcher, engineer, and project manager of IceCube.
What we're looking for are these very elusive subatomic particles called neutrinos. In order to capture neutrinos, in order to capture their signature, we need to instrument a very large volume of something like ice or water. And it turns out that the ice at the South Pole is just ideal for this project. There's an ice sheet there that's about 3,000 meters thick. And so we bury our sensors, our what we call optical modules, in the ice up to 1.5 miles deep in that sheet of ice. We've been drilling for 3 seasons. Our first season we drilled just 1 hole. Last year we drilled 8. This season we were able to drill 13. So we've got, if my arithmetic's right, we've got 22 now. We have a plan to drill 80 of these holes. The ultimate goal, we would like to instrument about a cubic kilometer of ice. The ice actually constitutes our telescope.
IceCube is an international collaboration of over 20 institutions that, with the goal of building a neutrino telescope down at the South Pole. It's believed that gamma ray bursts, actually black holes, not actually from the center but from the periphery, or supernovas are sources for the neutrinos.
We designed a rather enormous drill to drill the 60 centimeter in diameter, 2.5 kilometer deep holes. And our drill is based on a very simple concept. You heat up water and then you pour it on the ice and the ice melts. Although that sounds very simple, it actually is a very complex system. We have about 1 million pounds of equipment that constitutes our drill. We heat up water in a very big fashion down there. And we pressurize that water to almost 1,000 psi. And that's what we run through our hose, and then that's how we drill our holes.
What's this? This is a large hose reel holding approximately 9,000 feet of hose on it right now. This is one of the advantages of this new system. It allows us to use a single reel to have the entire hose on it so that you can drill to this depth. This will allow us to do it in one shot, go down to depth and come back up.
So it's high pressure, hot water, and it's at a very high flow rate at 200 gallons per minute. This is really the business end of the detector. It's called a digital optical module, or a DOM. This is a DOM, so I usually describe it as basketball size. It's actually just slightly bigger than that. And the basic construction of our telescope will include some almost 5,000 of these sunk into the ice. So we connect 60 of these to an electrical cable and then drop them down each one of the holes that we drill. The DOMs are made of purchased components that we have designed or particularly specified, and then all of those parts are then shipped to 3 locations where they are put together. We use a word integrated, so we integrate modules here and then we put them through an extensive test in a freezer lab. That's done here at the University of Wisconsin at the Physical Sciences Lab out near Stoughton. This is the business end right here, this hemisphere, and this is where Cherenkov light is actually detected by a photomultiplier tube, which is the shiny thing here inside the glass. The photomultiplier tube is basically a light bulb in reverse. You can see there are some electronics boards here in the upper hemisphere, including what we call our main board, and that's basically a mini computer which digitizes the analog signal that comes into it. It's a low-level signal that is then shipped up our electrical cable. We invest heavily in upfront engineering to minimize cost once we get into production. We would like to instrument about a cubic kilometer of ice. The ice actually constitutes our telescope.
Over time, people have found different ways to make a picture of the sky. What we are doing is taking a new picture of the sky, but we don't even use light. It's radiation that's made out of a beam that's made of particles, which are called neutrinos. Atoms are made of particles. In fact, you learned in school that atoms are made of nuclei and electrons, and nuclei are made of neutrons and protons. In fact, there is a critical fourth particle, which is the neutrino. And that's actually the particle we are using. And it has very special properties. Basically, you know, it can travel through walls, through lead, through everything. You basically cannot stop it. And its role is mostly to convert neutrons into protons, which is a nuclear reaction. So it's an agent that makes nuclear reactions possible. And of course, nuclear reactions are important. Without nuclear reactions, there wouldn't be sunlight and we wouldn't be here. And in fact, without nuclear reactions, stars wouldn't burn and explode. And you know, we are made of stuff that comes from stars that exploded. So neutrinos, even though they are essentially invisible, they play an absolutely critical role. Also, besides light, they are the most common particle in the universe. They are the only radiation that can travel to the Earth. So what we do is, from the South Pole, look at the sky at the other side of the Earth. And every particle we see comes through the Earth, so we are sure it's a neutrino. Just like light beams, neutrino beams don't bend. To make a picture of the sky with neutrinos, you have to capture them. And you know, just like your eyes tell you where the light comes from, you have to have equipment that stops the particle and tells you where it comes from. Blue light is how we see every neutrino. Millions of them fly through our detector every second. It's only 1 in a million that actually we can stop. And what happens is that it crashes into a hydrogen atom and make a very small nuclear reaction. So what we are doing is looking at the blue light of a nuclear reaction that's made by a single neutrino in a hydrogen atom. The blue light tells us there was a neutrino, and from the pattern of the light we can tell where it came from in the sky. They will point straight back to where they come from, and so we will then find out what the source is. They may have been produced way back in time, so it also has some relation to how the universe evolved.
The way it works is the neutrino travels to us from somewhere off in the distant universe, and it arrives at the Earth, and then it starts to head through the Earth. So a lot of them at some energies will just head straight through the Earth, but then some of them will happen to collide with a proton in a piece of rock. And so when a neutrino collides with a proton, what happens is it produces a secondary particle called a muon. Now a muon is just a particle which is really just like an electron. So we're all used to electricity. Electrons are just flowing electrical lines. So muon, you can just think of it as a heavier version of the electron. It's essentially the same thing, but it's just a much heavier particle. So it has some different properties to the electron. It will travel much further for the same amount of initial energy, for instance. If you've ever seen pictures of the core of a nuclear reactor, for instance, you may have seen pictures where they look down into the core, you can see the fuel rods and the control rods, and you see this blue glow in these photographs. Well, that's actually Cherenkov radiation. It's exactly the same type of radiation that we're detecting. And so what we can do is we can measure the time that the light arrives at each of the detector elements in the detector. And from knowing the time of arrival, we can then very precisely, we know the shape of the shock wave, so we can infer the direction the particle came from. And so we detect them by looking for their flashes of light and then taking all that information using a computer to reconstruct the direction the particle came from. So then that points back into the sky from potentially the source where the particle came from. So we're able to do a type of astronomy with the neutrinos because they travel in straight lines like photons do, like optical light does. What I'm interested in is analysis of the data. So my responsibility is overseeing all the analysis efforts of the collaboration. There's a lot of mysteries in high energy astrophysics. Despite some of the claims that you hear about scientists knowing everything, every time we discover something it creates 10 more questions. Gamma ray bursts, these are very highly energetic objects that we're really not real sure what's going on. Satellites observe them in high energy optical radiation, and so we're trying to see if we can see neutrinos from them as well. In fact, that's an interesting story about how they were detected, because back in the late 60s and early 70s, the US put a bunch of satellites into orbit to look for gamma radiation to try and check that the Russians weren't setting off nuclear explosions in the atmosphere, because a nuclear explosion will produce gamma radiation. So they put up this series of satellites orbiting the Earth to look for these explosions from the nuclear bombs to try and check that the Russians weren't setting off bombs. And in order to calibrate these instruments, they figured, well, there's no nuclear bombs coming from space, we'll just turn them around and point them into the sky, and we'll just sort of get what a background zero reading would be by looking. Obviously there's no nuclear bombs in the sky. So when they turned these things around and looked at the sky, they actually found there was signals coming from the sky. So the gamma ray bursts were discovered that way, just completely by accident. And it turns out that the Russians at the same time had made the same discoveries by spying on the Americans as well, by calibrating their own satellites. And then the other interesting thing was, because it was all a classified operation, it was many, many years before scientifically they ever announced to the science community, hey, we've discovered these gamma ray bursts.
We are going basically to investigate the most powerful engines of the universe, like for instance, at lower energies we have cosmic rays that are measured by satellites. So the particles that are produced in the universe and propagate in our galaxy, they can be detected outside of our atmosphere. But then when the energy increases, their flux becomes lower, and then we need to have huge detectors, and they are ground-based arrays that are called extensive air showers. Well, this is to show you that even in regions of very high energy, like 10 to the 20 electron volts, which corresponds to the energy of a tennis ball, we really have still particles produced in our universe, and no one understands who are the sources of these very high energy guys. So the strong connection between the cosmic rays and the neutrinos is due to the fact that they are produced by the same sources. And so we hope to understand, by measuring the neutrinos, the mysteries in the very high energy region.
Tied up in some of the cosmological questions, there's this idea that most of the universe is missing somehow. The universe seems to be made up of about 5% ordinary matter, sort of the stuff that we're made of and the things around us we can see and the stars and galaxies are made of. And about 20% or so is made up of dark matter. And so this is stuff that we don't know what it is. You can sort of tell that it's there by the way galaxies rotate and things and the way the universe interacts with itself. But we really don't know what the dark matter is. And also there's a concept of the dark energy. Basically the other 70% of the universe's energy density is some strange effect that it's actually making the universe expand faster and faster.
Most of the matter in the universe we cannot see, we don't know what it is. Neutrons, protons, electrons and neutrinos, guess that makes the matter we know about, but it's a tiny fraction of the matter that makes the universe. Our detector can actually observe dark matter. The way it basically works is that the dark matter, which we know fills our galaxy, it gets over time trapped in the sun. And so at the core of the sun there's a high concentration of dark matter, and these particles somehow manage to make neutrinos. So what we are doing is looking at the sun for neutrinos that have high energies and tell us about the dark matter. About twice in a century there is a star that explodes in our galaxy. Now this is something we're all waiting for. And so we have a whole system, special system set up in IceCube for an event like this. You know, if we are ready, if a star explodes within our galaxy, to record all the data from it. And in fact, when a star explodes, you get such a dense material at the core that the light doesn't get out. So the telescopes don't see it. But the neutrinos, of course, that get out of everything, get out of the star hours before. And so our hope is actually to detect the explosion of the star and then send the information, alert all the telescopes on Earth so that they can know it's going to come and possibly point at it. There was such an event in '87, but it was not in our own galaxy, so it was very weak. We only saw 20 neutrinos. We hope to see thousands with several experiments that are running now, including IceCube.
You often find that things that you've always thought are useless pieces of research tend to produce useful things that you never ever envisaged that you were going to discover. I mean, 100 years ago or so, people were doing seemingly useless experiments with no possible practical application involving electric currents and magnets. Okay, and then that's the whole principle of the electric generator. You know, you rotate an electric coil in a magnetic field and you get current coming out. That's electric generation. I mean, do we think, you know, the people who were originally doing these things just for curiosity, you know, probably never ever envisaged everything we'd have today because of that discovery?
The simple fact is, and Japan found this out after the war, if you only do applied science, trying to make money, after a short time you become an underdeveloped nation. Japan realized this, making big investments in fundamental science now. My favorite example is my previous job before the University of Wisconsin was at the Center for Nuclear Research in Geneva, Switzerland. And so they were doing a particle physics experiment that was probably more esoteric and more uninteresting to the public than IceCube. But in order to, it was made out of 3 universities, not 33. And in order to make the collaboration possible and to analyze data together and to exchange information, they built something that's now called the web. So by doing a particle physics experiment, we discovered the web. Now I don't have to tell you that the web, how important it is for the US economy right now. Fundamental science is absolutely essential to create the most interesting spin-offs.
So it really brings us to the regions that are explored by very few people in the world.
We'll build this, and then we're going to detect neutrinos, and over time something unexpected will probably be discovered. I mean, this is many times referred to as a discovery instrument. And if history is any indicator of how these things go, as you push your ability to detect things at higher and higher energies, unexpected things are discovered. That was true back, say, in the very early 1900s with X-rays, and we all know where that led to ultimately. Unanticipated things will occur when you look, and so we're looking.
In some ways, what MRI does is measure how much hydrogen you have in your body. And there's a lot of hydrogen because we have a lot of water in our bodies. And there's a lot of interesting things about the MR signal and how it differs between whether the hydrogen's in free water or whether it's near proteins, perhaps in, say, cell wall. The hydrogen in your body, you could model it to look like a little tiny bar magnet, a north and a south. And these little magnets would have all types of orientations, so there would be no net magnetization. However, if we put you in a really strong magnetic field, we can create a net magnetization. Now that net magnetization can be perturbed, and we can measure that. So we perturb it with a radio frequency signal. The interesting thing is, again, these tissues, this phenomena, will return to equilibrium at different rates. And that's what allows us to get very high amounts of contrast between different amounts of soft tissue. So you're familiar with X-rays where you see primarily bone and soft tissue. But in MR, we can create lots of different types of contrast based on the interactions of hydrogen, whether it's in free water or whether it's near macromolecules. What I just described is the signal in MR, but the difficulty in MR is really somehow making an image out of that information, because in that process we really don't know where the signal came from. There's an interesting property that the frequency that creates the resonance in MR is proportional to the strength of the magnetic field. So during these imaging experiments, we put a gradient field on, and we can put these gradient fields on in each of the three directions in your body, from left to right, from back to the front of your body, and from the head to the toe. And then, just as like in a piano, where you know that when your hand moves to the right in a piano, you're going to make higher notes, and to the left, you're going to get lower notes. In a way, we listen to the notes, and then we do an electronic analysis of the notes, of that signal that comes from the notes, and we can determine how much energy was at each of the notes. Now, that's very interesting because, in a way, compared to other imaging mechanisms that we have some experience with in everyday life, X-ray or ultrasound or computed tomography, those are all based on geometry. You fire in some energy and you see whether it gets transmitted or reflected in the case of ultrasound. In MR, we use very long wavelengths on the order of meters, but we're able to image on the order of less than a millimeter. And the way we do that is with this encoding. And so while that's interesting, it's also slow, because we can only take on the order of maybe 1 to 10 measurements at a time, where a CT system, you hear these commercials of 64 slice CT scanners that are being used to image the coronary arteries. Those will each row will have 1,000 detectors, and 64 rows, that's 64,000 detectors. So there's massive amounts of information that are taken in an instant. Where in MR, we're very limited, because we're in a method, in a way, indirectly sampling the energy that's at each of the positions in the body. And so much of the research that we do in MR is how do we accelerate this encoding of spatial position? How do we accelerate where the energy is coming from so that we can make images either faster for faster clinical sequences, or on the order of the physiological motion we're interested in, for like the heart. My background includes a lot of training in signal processing, biosignal processing as an electrical engineer. Here at Wisconsin, I'm on the faculty, the biomedical engineering faculty, as well as medical physics, and I have a courtesy appointment in radiology. So the ideas that we use to sample this space, this cube, with these radial mechanisms are really a background of understanding physics and a background of understanding signal processing. Same things you might use in communications. But then to be able to apply them and understand where these make a clinical difference, we need to have physicians who also have some understanding of the imaging modality and how it works. So I work closely with Dr. Rick Kajowski, a musculoskeletal radiologist in the knee, and Dr. Fred Kelch, who is our body specialist who helps us out in the breast imaging. This project started when we were looking at this vessel here, the popliteal artery, and our initial plans were to image that artery without contrast. And then upon looking at the images and how clearly we saw the cartilage, that grew interest in being able to image cartilage. And likewise, we then got curious about how it would look in terms of breast lesions. And we've also been looking at it then with patients who have had mammograms that are questionable and conventional MR exams of the breast. So we worked through the hospital to get this approved, and then we were able to image some volunteers, both healthy volunteers and those who had some knee pain. When that looked promising, we started penning these exams onto patient exams with their consent. And to date, we've done about 300 patients at our outpatient facility at Research Park with the 1.5 Tesla scanner, and about 25 to 30 at the 3 Tesla scanner. The research in my lab looks at acquiring this 3D cube in a different way. Normally, we raster through this space, similar to the way a TV screen is painted, row by row by row, through the cube. We've been looking at ways to go through this space like a cush ball, like a toy where the strands are very dense in the middle and then more sparse around the exterior. Now, in cases of vascular imaging, that has some big advantages in that we can do undersampling. We may not have to take all the data to fill in the cube because of some of the parameters of this method of imaging. What we're interested in this project, in the knee and the breast, is we can create very high levels of signal that stay around with a type of imaging called steady state. So normally we do kind of pulsed experiments. We put in a pulse of energy, we listen, and then we let the system recover. And that recovery can take much longer than the actual imaging. With this system, instead of letting it recover on the order of seconds, we do experiment, finish the mini part of the imaging in only a couple milliseconds. But then we immediately can image again. So to be able to do this requires that you be able to encode this signal very quickly, and that for it to work reliably, you have to be able to encode the signal within 2 to 3 milliseconds. Now, with these Cartesian techniques, because of the way they have to prepare the magnetization and then return the magnetization after the experiment to this equilibrium state, there's a lot of wasted time. And so it doesn't allow for much time for actually encoding the piano. We can only look at a couple keys in the middle. So in this mechanism that we've been working in our lab, we actually image during the preparation, and when we return the magnetization to prepare it for being back in the equilibrium state. This allows us to sample a much larger number of piano keys and make images of much higher resolution. What we're looking at here is a cube or stack of images, and each of these orientations allows us to cut through the cube in a different orientation. And so as I move through it, I'm displaying a different slice of the cube, a different cut through the cube. And so here, as we move over into the center of the knee, we can start seeing some of the interface of how the femur cartilage interacts with the kneecap right here. Likewise, we can look at the interface of the femur and the patella in the transverse cuts over here. So we have one other view we can look at, the coronal view, which looks as if the patient were laying down and we were looking down on the leg directly. And here, again, we can step through the interfaces of the cartilage of the femur and the tibia. We can see some really fine details in where this joint fluid there provides really good contrast for the cartilage. We see some points here where the fluid is actually going right to the bone. The advantage of this type of imaging is we get very high resolution on both this cut, the transverse cut of the knee, and this cut, the sideways cut of the knee. So we can get different views of different types of degradation and different types of pathology. Normally, the slices are imaged so that they're designed only to be viewed in terms of one orientation. So this image would look good, but this image would look very blurry. This is a image set from the conventional technique where 26 slices are used to cover the breast. In our technique, we're using 320 slices. So you can see in this view, the sideways view, resolution is okay. But because the slices are so thick to cover the breast, and really they have to be to use this technique to be able to complete the scan in a reasonable time. Here's the resolution in the other planes. You can see very difficult to make any discernible information from them. It's not useful for a physician to image a knee at only 1 millimeter resolution. The structures they want to see are much finer than that. And so the ability to use these techniques that we've developed then allow us to use the steady state signal and get to resolutions anywhere from 1/3 of a millimeter to 1/2 a millimeter. The conventional techniques that are used now acquire a set of images through the knee. It might take 3 to 4 minutes, but they have several gaps in between them, and the dimension of the slices is maybe 4 to 6 times bigger than the in-plane dimension. So if you have small defects, you often won't see them because they're averaged together with healthy tissues in these thick slices. What we do is study the whole knee in very thin slices on the order of 1/2 a millimeter. So we do not have the problem of averaging healthy tissue with diseased tissue or just degraded tissue in the case of osteoarthritis. So our improvements in time at our 1.5 Tesla scanner are in the order of twice to 4 times faster than a conventional sequence. With the conventional sequence, you'd have to repeat this 4-minute scan 3 times to get the information you'd want. Where here, we can get smaller voxels in all 3 dimensions in 5 minutes. Now, when we take that with new devices, new MR receiver coils, they're little antennas that are picking up the signal. Our technique works very well as the antennas get smaller, as you use more antennas to pick up the signal around the knee. And there, at stronger magnets at 3 Tesla, we can make another factor of 8 in improvement in terms of resolution per unit time. And there we're able to get down to as low as 1/3 of a millimeter isotropic voxels. What our new work is doing is we started just looking at cartilage degeneration and being able to image that. But as we get to better and better resolution, we've noticed we can see other problems that have to be examined through other imaging sequences in a knee to see if you have ligament damage or if you have a meniscal tear that's causing your pain. If this pans out, then we could replace the whole 30-minute knee exam that's done today with this one 5-minute scan. So the outcomes of this work are outcomes in technology development. Most people associate science with hypothesis-driven research. And the National Institutes of Health, through the National Institutes of Biomedical Engineering, NIBIB, have looked at this and said, a lot of what we ought to be doing is developing technology to be able to look into problems. And so that's a lot of what our lab does, is develop technology so that we can assess either new biological areas of the imaging or to be able to do things, capture motion in MR that we might have to do otherwise with X-ray or poor resolution. So the outcomes of this research are methods to be able to use these new imaging paradigms in a robust method. Now, having said that, the outcomes of this in terms of clinical impact, new methods are being used in early osteoarthritis to see biological changes. The content of proteoglycans, which are early markers of osteoarthritis degradation. Now those take a long time, and it would be impractical to put those studies onto a traditional 30-minute knee exam. So what we might be able to use the clinical impact for this is to reduce the scan time from 30 minutes to 5 minutes and then use the rest of the imaging time to look at these early markers of degradation. Or we could look at seeing imaging longer and then try to get to very fine resolution, like 1/10 to 2/10 of a millimeter, and see if we can see early changes of osteoarthritis that start giving us indicators of how cartilage degrades. In the breast, there's a lot of interest in using MRI. There's local national stories this week about how the National Cancer Institute is suggesting that women who have certain genes or who have family histories of early breast cancer get an MRI every year. The problem with MRI is it sees every lesion in the breast, but it sees a lot of them are benign. And so at that point, the physician is left with doing a number of biopsies. So it creates a lot of work for the healthcare system, a lot of expense, and a lot of trouble and concern for the woman who's being examined, in this case every year, who then may have to have some painful biopsies and a kind of long, drawn-out process. Our mechanisms with these 3D imaging and very high resolution in all three planes allow us to see some really fine structures which are signatures of benign tissue. So the plan would be to append these methods onto the conventional breast study, or really even replace current ones that are currently being done. And then we would be able to increase what we call the specificity of MR exams so there were less unneeded biopsies. So the pathway to how this gets to clinical practice is rather interesting in that the NIH and certain foundations are very interested in moving beyond basic science to clinical care, showing the taxpayer how their money is being used to improve their care. So some of this work was funded by the Coulter Foundation, who is interested in not necessarily basic science, new research. What they're judging us as a university in is how we take our ideas and move them into clinical practice. So we use that to work on improving the robustness, the reliability of these sequences, and shortly these sequences will be moving out to a number of other hospitals at Stanford, the Mayo Clinic, Toronto, and Michigan State. And physicians who are unrelated to our research program will be assessing the impact of this work. And then with that, the vendors who would then make investments in this technology, they would have that to go upon, and then they could decide whether they want to put that into their clinical package. Where we're taking this work in terms of the musculoskeletal system is if we work at even higher resolutions, then separating the fat and the water may not be as important because we'll be able to see other markers for that. So I have a student working on that to try to get down to 0.1 to 0.2 millimeter resolution. Another thing we might be able to use this for is to image sodium. And sodium can be a marker for the concentration of proteoglycans, which start going down as cartilage starts being degraded. And we could see that perhaps before we'd see morphological changes in shape. Otherwise, in terms of the vascular imaging, we have a program in interventional imaging so that we can, that we're using in the treatment of liver cancer. So we're working to build a system so that the images can be reconstructed in real time and visualized in real time for all three spatial dimensions and time. So the thought is that in treating liver tumors with chemoembolizing drugs, you make very targeted treatments that treat a portion of the liver that's fed to the arterial system of the liver, where cancers typically grow. By being able to see the tumor and being able to see the vascular system, which you can't do in X-ray fluoroscopy right now, we could direct the treatments to a much smaller region of the liver and produce more targeted treatment. And if these kind of things work, then these ideas would be applicable to all types of drug delivery, where we used MR to guide the delivery so that it was more targeted, more local. See where we are delivering stem cells or other biologics.
The CMS experiment is one of two experiments located at the CERN Large Hadron Collider. This is a laboratory on the boundary between Switzerland and France near the city of Geneva. And it sits on a ring which is called the Large Hadron Collider. It's a ring of superconducting magnets about 27 kilometers in circumference, and it contains beams of protons that collide with each other. And when the beams of protons collide, they produce particles, and we analyze those particles in the compact muon solenoid experiment.
When protons on protons collide, the constituents of the proton are actually colliding. Those are called quarks and gluons, and they have very strong interactions, as we call them. So we, in fact, will have 1 billion interactions every second of these constituents of protons and protons. And the events that we're interested in have these particles called muons. These muons are like electrons but heavier, and they interact weakly and electromagnetically. They travel through the entire detector. There's a large detector that we have built with lots of steel plates in it, and muons traverse all the way down.
How do we actually find particles as they pass through our detector, and what do they look like, and how do we actually detect them? Because this is a rather complex operation. But if you start, what happens is that the beams collide with each other once every 25 billionths of a second. And they collide with hundreds of billions of protons, but only a select few actually collide with each other. Bunches of these protons, counter-rotating bunches, pass through each other, most of the time unperturbed, but every once in a while the protons, or as we discussed, the constituents inside them, the quarks and the gluons, actually come in contact, and you have a collision, and then the debris of that collision surges out through the detector. And the first thing it runs into is something which calls a tracker. The tracker, as you might understand, looks for tracks. And how does it do this? As the particles pass by through pieces of silicon, like the chips that are in your computer, they strip off electrons from some of the atoms in these silicon pieces, and then you have a charge produced. And you detect that charge just as you would see the charge inside a computer chip. And that gives a little signal which we then detect electrically, and we then send that signal out, and that becomes a piece of the track. But we're not done yet. There are other particles which can still pass through these crystals and not leave much of a signal. So we then, outside of that, we place some brass, cartridge brass from artillery shells actually, and scintillator, which is plastic that gives off light when particles pass through it. And we collect the signals from that. This is all inside what is probably one of the world's largest magnets. It produces a field that is 4 Tesla strong. It's about 13 meters long and 6 meters in diameter. Why do we use a large magnet? Because we want to charge particles bend in a magnetic field. And so in the magnetic field, as they bend, the slower they're going, the more sharply they bend. The faster they're going, the less sharply they bend. So we can understand how fast the particles are moving. We not only know where they went through, we can look at how much they bend in the magnetic field and figure out how much energy the particles had. In the calorimeters that I described before, the brass scintillator and crystal, we look at the amount of light that gets produced. We can look at the amount that the particles get bent as they leave their tracks in the tracker inside this magnetic field. But we're still not done. Outside the magnetic field of the solenoid, there are some particles that can even make it out that far, and those are called the muons that my colleague talked about just a minute ago. And those muons pass through a lot of steel, and they're the only things that pass through a lot of steel that we can detect easily. And so we look for their tracks in other detectors which contain, in many cases, gas, and they strip the electrons or ionize the atoms in the gas and make little electrical signals that we again observe. And so this is the last stage of particle identification in the detector. And so those are the tools we use, and that's how the detector is put together.
When these interactions happen, when you have large number of these strong interactions, we also have a few very rare interactions which we are most interested in. And those interactions will tell us more about the structure of matter, of various types of particles we have. Strong interactions are very simple and very nicely described in a theory. It's difficult to calculate things in the theory, but it's very nicely described. Whereas the weak interactions, which we also know are have much more complex nature to them. And in order to elucidate that, we have to look for these very, very rare events. So the weak interactions, as opposed to the strong interactions, require particles which have large mass to explain why the interactions are actually weak. And in order for that mass to be there, there should be a new particle which we call the Higgs particle. And this Higgs particle acts like slush. When you walk through slush, you slow down. So everything slows down when walking through this Higgs field. So all particles attain mass by slowing things down due to these interactions with the Higgs field. So this is a fundamental particle, and it has to be there in order to provide mass for the particles which mediate weak interactions and all other particles, in fact. So the Higgs boson plays a very fundamental role. Because of that, we really must find the particle. And in addition, the Large Hadron Collider energy is set up so that if there is such a particle as Higgs boson, it will be found at the Large Hadron Collider. If there is no Higgs, if nature throws us an even bigger surprise than what we are hoping we'll find, we would still be able to do a lot of experimentation there. There will be interesting phenomena which will happen, which shows that Higgs is not there, but something else which takes the effect of Higgs field is there. In addition to that, the theories which describe the Higgs boson require some additional new phenomena, which we call supersymmetry, for instance. And this relates to even larger questions. For instance, we know that in the universe there's a lot of dark matter. In fact, the visible matter that we are all made of is a very small fraction. It's the dark matter which dominates in the universe. And the fundamental theory that we have right now does not have any particle which could explain the dark matter. Whereas these new theories, which will help elucidate the Higgs boson phenomena better, actually have candidates for this dark matter. So one of the things that we're looking for in addition to Higgs boson is to look for supersymmetry, look for dark matter.
The University of Wisconsin High Energy Physics Group became involved in the compact muon solenoid experiment following the cancellation of the superconducting supercollider down in Waxahachie, Texas, where both Professor Dasu and I were working very heavily on that experiment. And again, it was to explore the energy frontier at the highest energies to look for the Higgs and for supersymmetry and many of these other effects. The European groups had formed at the Center for European Nuclear Research at CERN, the Large Hadron Collider project, which had the compact muon solenoid experiment. And we went and talked to them, and we were developing many of the technologies and instrumentation techniques that they needed for that project but had not developed yet themselves. And after some discussions, we, as a group, decided to join. And when we joined, we brought with us various competencies, which we then used to help them and to help get the experiment done. And that included expertise in high-speed electronics, vast amounts of data processing of all these signals we've talked about coming out of the compact muon solenoid, and also quite a bit of adept mechanical engineering abilities, which allow us to make these very large steel structures that I spoke of earlier. And we were also responsible for, and the University of Wisconsin was responsible for, building, for example, the end cap discs, which are these very large discs of CMS that are many meters high and weigh hundreds of tons. And we're done under contract, a world contract, in fact, in Japan and in China, and other structures were built in Serbia and all over the world, and then gathered together in one place in Geneva and installed in the experiment. When the experiment goes online, we expect a long period of data taking. We expect 2 phases. We expect the first phase where the Large Hadron Collider reaches its full brilliance, and which means the largest number of collisions per second, and that period will take about 10 years. We're searching for very, very rare phenomena, and although we have millions and millions of collisions, they don't happen very often. They just happen, we may get 1 billion collisions per second, if you can imagine that. But maybe only a few of these Higgs particles get produced per day at that rate. And we need a lot of them to distinguish a real signal from a signal that could be caused by fluctuations. And so we will run for about 10 years of data taking. After that, we will have an upgrade to the project to allow the brilliance of the machine to go up by another factor of 10. And we'll run probably for another 10 years after that. So it's a very long period of data taking. And the real challenge of the data taking period that comes after that is to refine the analysis of the experiment, to learn as we learn about the collisions at these energies that we've never seen before, and then to process that data and extract physics out of it, out of this huge and very complex detector. There are almost 50 countries on CMS. There are about over 2,000 scientists, this includes students as well, working on it. And we must collaborate together. And the complexity and dimensions of the detector and the vast quantity of data require a huge effort by many people who specialize in each different aspect of the detector and in the understanding of the physics and the models of the physics. And so what happens is we organize ourselves into groups to work on specific problems having to do with the data analysis, and then look for these rare signals of new physics within the data. And it takes many teams and many large teams to extract the data.
Every time a collision happens in the CMS experiment, there are about 1 billion sensors which are looking at that particular event. Only a small fraction of them will actually have a signal that we record. But even that adds up to about a megabyte or so of data every event. But there are 1 billion of them every second. So that's a huge amount of data. And each of those snapshots needs to be looked at, and we have high-speed electronics which looks at those pictures and decides some of the pictures are interesting. Eventually we have about 150 pictures every second which are interesting, which we need to transport. Even that is very large volume for every analyst in the world from CMS, 2,000 people to get. You can't put that on your laptop by any means. So we need to further reduce it. So we have complicated programs which we run on it, and we digest the information and annotate this picture saying that this is an interesting event because it has got 4 muons. There's some other event which is interesting which has got 2 photons in it, and so on and so forth. Now, if you're looking for Higgs decaying into 4 muons, you really don't want to look at the rest of the billion events. You only want to look at the small stream. So we collect that stream and bring it over. So depending on what the physics interests of various people in the collaboration are, you register to get only those streams of events in great depth. But whenever you look at a certain class of events, you also need to have the full bulk events so that you can actually understand what the background to those things is. But we can't get all the data, so we get only the summarized data for those. So we basically will have about 1 billion events per year imported in Madison, but for most of the events we'll only import some summary information. But for those events that we're really interested in, we import more information about what the details of which element of the tracker actually fired, so we can maybe improve the reconstruction, maybe measure the momentum of the muons better, for instance. In order to prepare for this large onslaught of data that will come once LHC starts taking data, we've been preparing various challenges. We call them Computing and Software and Analysis Challenge, 2006, 2007, and so on. So every year we have a challenge for the past 4 or 5 years. And increasingly the challenges are getting more and more complicated. We're at the level of about 10% to 25% right now. So we're able to transfer about 100 megabytes a second or something like that, whereas we could in principle transfer 1 gigabyte a second if we completely use up the network. So we're able to actually demonstrate that we can move files around. So at the moment, since we don't have LHC data coming in, what we're doing is that we're generating data on our computers here in Wisconsin, and similarly people at other collaborating institutes are generating data and shipping them all to CERN in Geneva. So they go to the central place in Geneva, and now we pretend that that's real data, and then we ship it all back out to various tier 2 centers, which we are part of, and we get data from CERN to simulate the downloading mechanism. And all of this is being done on this Boreas network that we have. And we're able to fill up 1/3 of one of the fibers that we have access to. And soon we'll be expanding it to cover larger than 10% level that we're exercising right now.
Data from experiments performed in Switzerland are transmitted to Fermi National Accelerator Lab in Chicago via a commercial circuit, at which point data from Fermi is then transmitted to Madison via the BoreasNet network. The BoreasNet network has capacity of 400 gigabits per second, which is divided into 4 chunks of 100 gigabits. This fiber is architected in a 1,200-mile ring that includes Madison, Minneapolis, Ames, Iowa, Des Moines, Iowa City, Iowa, Chicago, Milwaukee, and back to Madison. BoreasNet has lit the 1,500-mile network using a technology called Dense Wave Division Multiplexing, or DWDM. Using this technology, the BoreasNet network is able to transmit as many as 40 different colors, or lambdas, across a single pair of fiber at the same time, allowing multiple research projects to occur simultaneously. Researchers will move approximately 120 terabits of data between Fermi National Accelerator Lab in Chicago and Madison, Wisconsin. That flow of data will occur at roughly 4 gigabits per second over the course of many hours in a day. To get a sense of how large a 10 gigabit per second circuit is in comparison to other communication options, we look at downloading the DVD version of the movie The Matrix over 56 kilobit modems that many people use across the United States. It would take approximately 171 hours to download the movie. Over more current DSL or cable modem infrastructure, the movie still takes over a day to download at approximately 25 hours. Now, using 10 gigabit circuit connectivity that UW researchers have access to, the same DVD version of The Matrix could be downloaded in less than 30 seconds.
So a lot of data has moved back and forth. The way we organize these things is that we have a team of people and a certain amount of time set aside for doing these tests. And oftentimes the tests are linked to some useful work in terms of preparing our software for actual ultimate data analysis. So we're not just simply moving data around, we're actually producing some LHC events which are interesting for us, shipping them to Geneva, and then downloading them back in Madison or in Fermilab or wherever, and analyzing them on our computers and simulating what's happening.
There have been many times in history when people have forecast the end of physics, and they've been proved wrong. So I think we take the lessons of history and say that in terms of particle physics,